Hello everyone and welcome to our presentation. My name is Daniel and today I'll be discussing our novel set-based technique to reduce ambiguities in shadow matching by iteratively processing GNSS pseudoranges. There are many reasons that you might care about urban GNSS localization, but for this presentation I really want to focus on the narrative of rideshare. I want you to imagine that it's the last day at Ion GNSS Plus and you just ordered your rideshare to go to the airport. In order for the rideshare driver to correctly rendezvous with you, they need to know primarily two pieces of information. First, which street you're on, and second, which side of the street you're on. A lower priority item is along the street where you are on, because they'll often see you on the approach. So if we're really focused on the street and the side of the street, then shadow matching is a well-developed technique to provide exactly that information. Shadow matching has two paradigms, grid-based and set-based. Grid-based shadow matching has been the dominant source of representation of shadow matching in the literature for the past decade. The key idea is that you lay a grid over the city, and then online you evaluate grid points in your vicinity, and you determine if those grid points are in the shadow or not in the shadow. So in this case on the left, the orange grid cells are in the shadow, the green grid cells are not in the shadow. In contrast, we can encode the inherent set-based nature of shadow matching if we use set-based shadow matching. So here we compute the shadow itself. So we compute the orange shadow as the set that represents the shadow. And here, anywhere in that set, we are in the shadow, or in the green set, anywhere we're not in the shadow. So in this case, we encode exactly the set-based nature itself. Now, Jozevich et al. Produced an early form of set-based shadow matching based off of rastering in 2012 and 2015, but it wasn't really able to compete with grid-based shadow matching in terms of computational efficiency or based off of the quality of the map. In contrast, our co-authors independently produced set-based shadow matching at last year's Ion GNSS Plus, where the whole framework is completely set-based. So even the map itself is set-based. Now, given that set-based shadow matching is so much newer than grid-based shadow matching, especially the form that our co-authors developed in last year's Ion GNSS Plus and then further developed in the navigation paper, why might you be interested in set-based shadow matching? Well, first of all, set-based shadow matching doesn't lose resolution across scales. So when the user first opens the app and they have a large uncertainty and large scales, they need to be able to transition from that state to right when they go to rendezvous, which is now lower uncertainty and smaller scales. So if you want to be able to easily transition across these difference in scales, set-based shadow matching might be what you're looking for. Another option or another advantage is computational efficiency, both offline and online, which is something that we discussed in our past ION work and the related navigation paper. You might also have downstream processes such as downstream filters or downstream motion planning options that require a continuum or require a set-based formulations of your state. So if you have that sort of system, then this might be a good option for you. Another key advantage of set-based shadow matching is that we encode the full shadow matching information, but we do that in the minimal representation. So this means that we encode the full set, so there's no gaps between grids, cells, and we do this in the minimal way possible, which means that we only have to include the shadows themselves. So we have no sense of redundant grid cells that are both in the shadow or both not in the shadow, and we have no sense of grid cells that have the shadow boundary right near each other, which creates overlapping or possibly conflicting information. And lastly, in our recently submitted work, we showed that we can embed risk awareness into this framework directly because we're able to exhaustively consider all possible classifications of shadow or not shadow using this minimal representation. But if we really want to achieve this rideshare goal of identifying the correct street and the correct side of the street, then we also have to deal with one of the key challenges of shadow matching, which is mode ambiguities. So this was illustrated in Groves et al. 2015, where they're laying out the challenges ahead in shadow matching. And they show that shadow matching can often lead to a multimodal posterior distribution, where it's ambiguous as to which mode is the correct mode for the user position. And this is a property inherent to shadow matching. It is not an attribute of the representation. So it's present in both grid-based shadow matching and in set-based shadow matching. Now, since the 2015 paper, a lot of work has gone into ways to reduce mode ambiguities in this grid-based fashion. So for example, this paper from Groves and Ajad in 2018 starts with shadow matching only, which has 3 modes, and is able to use the GNSS pseudoranges to arrive at 1 mode. Now, we would love to do this for set-based shadow matching, but unfortunately, as of now, there does not exist a method to use the GNSS pseudoranges in this set-based framework. So if we put this all together, with shadow matching alone, we've received a lot of attention both in the grid-based formulation and in the set-based formulation. But if we want to look at additionally reducing the mode ambiguities in shadow matching, all of the work has been in grid-based formulations, and none of the work has been in set-based formulations. So this paper is really identifying and tackling that research gap, where succinctly, we want to robustly reduce the mode ambiguities in set-based shadow matching. And we're going to do this in a 2-step approach. First, we're going to formulate the pseudorange equation in a way that's friendly to set-based operations. And then secondly, we're going to derive an iterative filter that's fully set-based, that's going to be able to take in that set-based form of the pseudorange equation. So going into our outline, we're first going to go into the methods where we talk about these 2 parts of the approach, the set-based pseudorange and then the set-based filtering. And then we're going to look at real-world data to validate our approach before going into the summary. So diving into the methods, this is the overall filter architecture where we start with modes from set-based shadow matching in the set-based 2D position domain. In the first part of the approach, we're going to build these set-based pseudoranges. So at each time step, we're going to take in the pseudorange measurement. We're going to form this set-based object that we're going to talk about in a moment. We're then going to pass that on to the filter. In the filter, we're going to start with a uniform uninformed prior. So this means that we have an equal probability of being in any of the modes. We're going to process in that set-based pseudorange information into this one-dimensional range offset dimension, which we're going to derive mathematically in a moment. If we have access to a line of sight classifier, we can even further improve this with additional urban awareness via the line of sight probabilities. We're then going to take a fused result of that one-dimensional range offset domain and push it back onto the position domain to arrive at a posterior distribution over our belief over the modes. So this means that we want to assign higher probability that we're in the correct mode in this posterior distribution. And we're going to do this iteratively by then passing the posterior from the previous time step into the prior for the next time step. So now we're going to go into that first part of the approach, the set-based pseudoranges. So this is our familiar form of the pseudorange equation, where we have the pseudorange on the left, the true range in the middle, and then the additional biases such as clock bias, multipath bias, non-line of sight bias, and additional errors on the right-hand side in red. Now we can merge those additional biases and errors into one term, which we're going to call the bias in the range offset. So this represents the offset between the true range and then the pseudorange. Now we're going to take inspiration from works from the 1980s and 1990s, where they were looking at analytical forms of the pseudorange equation that weren't iterative. So in those works, they formed what was called the squared form of the pseudorange equation, which is shown here. And the key idea is that we're able to arrive at a much more symmetric version of the pseudorange equation, where we have these differences that are then squared in each of the terms. And we can identify in blue a 4-dimensional satellite state. So this is 4-dimensional because we have the 3 dimensions of position with an additional dimension, which is the pseudorange. And we see analogously this 4-dimensional user state, which is 3-dimensional in the user position, but then also has this bias in the range offset. So we're going to use this because it's very convenient for this set-based operations. But because we're tackling urban GNSS problems, we really want to see how does this equation look like on the realm of the area of interest in an urban setting. So this is a conic equation, but when we look at, say, a city block, we see that this equation is basically linear for an area of interest of, say, hundreds of meters, and it's linear to within millimeters. So this plane basically says where in the user higher dimensional state space, so this 4-dimensional state space, is the satellite and pseudorange consistent with the user state. So this is this blue plane. Now we can assess the user state. Where could they possibly be in this higher dimensional state space? So in the 2D position space, we have some polygon that they might be in, some set-based representation. We also have an interval in the range offset, which captures the possible errors in the range offset. So this is shown as this green interval. To combine this information, we simply have to take a Cartesian product of the two to form this area of interest prism, which basically says all the possible user states that we could be in given this error. We now want to bring in that plane that we just talked about with this set-based form of the pseudorange equation. So we're going to call this plane the satellite pseudorange consistency plane, or spec plane for short. And we really care about what portions of the AY prism, which captures the possible user error, is consistent with both the satellite location and the pseudorange information. And that operation is this intersection, which is this dark blue object, which is itself a set in this higher dimensional space. And we can look at how this set projects onto each of the dimensions. So onto the position dimension, this projects as a spec strip on the ground. And we can also project it onto the range offset dimension to produce an interval. So importantly, this intersection is a set that allows us to go between the position domain and the range offset domain and vice versa. So now we're going to make use of that in the filter. So now we're going to transition to the filter and how it works. We start with the spec planes for each satellite, and that forms this stack of spec planes on the left-hand side. For this, to illustrate our filter, we're going to consider an example with two modes. And what we're going to do is we're going to take those modes and project it onto the spec planes, just like we discussed, and produce intervals in the range offset domain. And those intervals are each going to be a uniform distribution. And because we have two modes, we're going to be able to get two intervals per satellite or per pseudorange. And that produces the distributions on the right-hand side, one per each satellite. Now, the key insight here is that we care about where the satellites are in consensus. So this means where do they most agree on the range offsets. To do this, we can form a mixture model, which weights all of the satellites together and forms probabilistically where is it more likely. Now, because we're in an urban setting, we can do even better if we add in the probability that the satellite is a line of sight satellite, because if it's a line of sight satellite and it does not have additional multipath or non-line of sight effects, it's a more pristine estimate of our range offset. So if we have access to a line of sight classifier, we can further weight the satellites when we form this mixture model to provide this mixture model distribution on the right-hand side. Now, ideally, we would take this distribution and pass it directly onto the position domain. But at this point, the distribution is a bit more complicated. So instead, we can efficiently approximate this distribution as a collection of samples. And we find that for this example scenario, 500 samples is plenty sufficient. And what's nice is that these samples can be used completely in parallel. So specifically, to pass it back onto the position domain, we consider each sample as a count in a Dirichlet distribution to check whether we think that that sample agrees with the mode on the ground. And because it's a Dirichlet distribution, the marginal distribution of the Dirichlet distribution is a beta distribution, which is what we see on the right-hand side. So we started with an uninformed uniform prior over the modes, and now we see that we've arrived at this beta distribution on the right, where we've identified mode 2 is a more probable mode with 65.7%, and we're able to reject mode 1. And because it's a beta distribution, we're able to capture the uncertainty in the samples in this distribution. So now that we've seen how we combine this two-step approach, the set-based pseudoranges and the set-based filter, let's see how it performs on real-world data. And we really urge that you look at the paper for more complete results than what we have so far in this presentation. So going into the experimental setup, we want to return to that ride-share narrative. So we want to imagine that you just ordered a ride-share in the financial district of San Francisco, in this case, a heavily urbanized environment as shown in the fisheye camera on the right. And we're going to take the user to have a Pixel 3 phone using only GPS L1 signals at roughly 1 Hertz data collection rate. And we train offline a classifier using a TU cabinets dataset with a classifier accuracy of 75%. If we run set-based shadow matching as described by last year's ION GNSS plus work and the following navigation work, we arrive at these modes for shadow matching as we see on the screen. So in this case, mode 2 is the correct mode as illustrated with the star representing our true location. And we have these 5 other modes. In this case, if we just trust weighted least squares, it would predict that mode 1 is the correct mode. So we need to overcome weighted least squares, and we need to overcome 6 modes in our distribution to identify the correct mode. And indeed, our filter is able to do exactly that. So we identify that mode 2 is the correct mode, and we adjust the probability based off of our confidence using the pseudoranges available. And we find that this roughly settles in 35 measurements. And because the measurements are collected at 1 Hertz, this is roughly 35 seconds. Now we want to validate the different parts of our filter. So on the rows, we have the first part of the approach, which is the set-based pseudoranges. And on the columns, we have the filter design being iterative. So if we don't use iterative, we have a single step filter where we don't pass the posterior back into the prior at each step. And if we are able to use the line of sight probabilities from the line of sight classifier, then we're able to have this additional urban aware component. So the most important metric here is, are we able to identify the correct mode? And then we find that when we combine the set-based pseudoranges, the line of sight probabilities, and iterative, we're able to identify the correct mode in 100% of the time steps for this experimental scenario. If we drop one of those, then we see a degradation in performance, though dropping only one still has very high performance. So for example, if we keep iterative but don't use the line of sight probabilities, we're able to identify the correct mode in 99% of the time steps. And if we drop iterative but keep both the line of sight probabilities and the set-based pseudoranges, we're able to identify the correct mode in 95% of the scenarios. But note that if we drop both, then we're not able to identify the correct mode in very many scenarios, in this case, only 76%. Though that's still a big improvement over not being able to identify the correct mode at all. In terms of computational efficiency, we find that our filter is very fast, arriving at the prediction in only 9.8 milliseconds per time step. And we see that dropping information reduces the time, though it's roughly the same time per time step because there's roughly 1 to 2 milliseconds of variability. So we see that it's very computationally efficient. So in summary, we developed a set-based form of the pseudorange equation using this satellite pseudorange consistency objects, or SPEC objects. We then designed a fully set-based filter that's able to reduce the mode ambiguities in shadow matching using that set-based form of the pseudorange and additional line of sight probabilities. We then validated our filter using real-world data in San Francisco, and we show that we're able to smoothly identify the correct mode in all the time steps that we considered, despite there being many modes in our distribution, and despite weighted least squares being highly misleading in this case. So lastly, I would like to thank the National Science Foundation for funding this research, and the NAV Lab for being an incredible community and having such insightful discussions over this research. So thank you so much, and I look forward to seeing you at ION GNSS+. Bye.